So in this screencast, which can be taken part of the as part of the DSFT course that's on this playlist, but it could also be taken separately, I'm going to talk about functionals, and in particular, functional derivatives. So functional derivatives are not always as intuitive as the derivatives that we are used to in calculus. So I find this useful uh, to do this short screencast has it allows you to have some rules of the differentiation of functional differentiations. So let's get going. So first of all, let's define what the functional is. Functional here, like for example, phi. Uh, in this case, it's a function that's not just a function of the position r1, r2 to rn, which are the usual variables, really, but it's also a function of a function. It's a function of the density. So that function, of course, changes with in space. This is the R1, R2, and so on. But also, it's going to depend on what the density is. And in this course on DFT, that's going to become clear. That's actually going to be the cornerstone of the entire theory of DFT. So let's try to see what we mean by that. So I'd like to attract your attention that to make it clear, it's a functional of the function n. We use those square brackets. So the square brackets are very useful for that. So functionals. So we can say that a functional, it's really a rule or a map that goes from a function to a number. So we are very familiar that to go from a number to a function. That's what we are used to in calculus. But in a somewhat mathematically slopey way, because there are all sorts of conditions that you have to fulfill mathematically, but we are not going to worry too much about those here. I'm going to say that the functional of n, so again, in square bracket, is a function of a function. So f of n returns a number for a given function n. So for example, you are used to this other notation, which is just the normal parenthesis, that f of x, x being like a variable, like a position, for example, f is a rule to go from a number to another number. So an example of a functional would be, for example, the number of electrons, which is obtained by integrating the density over the entire space. So in that case, we say that that number is a functional of the density. So we can change the density and then we calculate the number that we are going to have, for example. So that's a very simple example of a functional. We will see that this functional in particular is called a local functional. We are going to see that in a second. So here n, the number of electrons, is a functional of the density. That's that simple. So as very often when we try to do theory or we try to make sense of advanced theory, we are usually stuck because we think that things are too complicated. But as always, in my opinion, 90% of the problem is related to definitions. So once we understand the definitions and the fundamental definitions and rules, things get much simpler. So that's really the objective of this screencast here. So here is another example of a functional, which is one that we see a lot in quantum chemistry and quantum material science, computational material science, is the Hartree potential. So the Hartree potential, we have a pretty good idea, intuitive idea that this potential is the electrostatic interaction between a point charge and a density of charge, really, n. Because you can imagine that you are basically the charge interacts with those small elements of charge all over the space. But this is complicated in the sense that n is a function, right? It's a density, so it's a function in the sense that it returns a number for every position in space. Now the Hartree potential depends on that function, and therefore it fulfills the criteria to be a functional. This is called the Hartree potential. We are going to see in a few minutes how we can get the potential from the energy. So that's going to be something that we will do by the end of the screencast. Now imagine that we want to calculate the functional variation, because very often in what we do in science is calculate variations and minimizing variation, maximizing variations, or monitoring variations. So we do that all the time. What happens now about a functional derivative? And this is really what this screencast is about. So let's imagine that we are considering a functional variation delta y, right? That's what we are interested in. Now, imagine that we have a function of one variable, right? The function of one variable, y equal f of x, and we have two types of variation of y, of course. One, we can vary x. So if we have vary x, of course, y is going to change, but that's basically the function. Or we can have the one associated with f. So if f changes, then y is going to change. This is the usual derivative that we are doing here. So for fixed functional dependence f of x, the ordinary differential dy is measured by how y changes as a result of the variation x plus delta x of the variable x. So the second one, the one associated with f, is the one we study here, right? This is when I say the usual one is the one we are studying here. It's the functional one. Imagine that you have that function, and then you stay at one place. You stay at one place x, for example, along the x-axis, and how the function varies depends on how the functional form f of x varies. This is what we are doing here. So this is very formal. Frankly, I have to introduce this in this slide. It can be debated how much information you get from these slides, because what's going to come now is going to clarify everything. So let's talk about functional derivative. So once again, the usual one that we are used to in basic calculus is the df over dx. So variation of the function f when we change the position x a little bit. So we are used to that, and the way it's defined is defined like this. So it's defined as the function at a small increment away from x, so f of x plus dx, is going to be the function at x plus a variation. And you can see that here I put the O dx square. Of course, O dx square is equal to 0 because d is infinitesimal, but I put there as a reminder of Taylor expansion. So if you have a Taylor expansion for finite variations, we would have a bunch of extra terms. Of course, we don't have them because the variation is infinitesimal, is dx. Okay, so this is something that you are used to. Now, the functional derivative s of x also measures the first order, if you think about Taylor expansion, about a change in the argument. So basically, what we have is something like this. So this is probably the fundamental equation that it's important to understand. That's basically, there's not much to understand if you understand the first one, but it's essential. So we are going to call the functional derivative Sx. We don't know what it is yet. We are going to define that in this screencast like this. The function capital F for the function small f plus a small variation of that is equal to the function of the initial function f plus a change, right? So nothing really surprising. And that change, of course, has to involve an integral. Why is that so? Because a change in the function lowercase f is going to affect the function from every single point along the variable x. So basically, what we need is that we need to sum or to integrate. Really, we have to consider every variation along the x-axis here. So I make it simple by having just one variable x, but this can be expanded to a large number of variable x, y, z, and so on. So this is what we have. Now the question is, what is s of x, right? The s of x is going to give you how the functional changes. All right. So it's important to know the integral is needed because the variation f is determined variations in the function, at all points in space. So good. So this is the function. This is basically what I just explained to you in the previous slide, the first equation. And the notation we use for S of x, so the one that's used to calculate the variation, is in the red box. So the notation is delta f of delta capital F over delta lowercase f is actually gives S of x. So when we talk about functional derivative, we really talk about what's in the red box. All right. So that's I think that's with this we can now look at this a little bit more in detail. Okay. Now suppose that we have a function and we want to calculate this. All right. So the functional derivative depends on the value of x where it's computed. We can define by considering total change upon the variation of f of x as a linear superposition of the local changes over the whole range of x values. So this linear superposition is nothing else than a translation in math or in English and vice versa of the definition that is in the black box. So basically we say that we linearly add, well, integrate really, but we linearly add all those variations for each point x. So I like this little plot that's on the right-hand side. So we start with f of x, and this variation of x plus delta f of x is written in orange here. And the point is, if I calculate a function, so capital F, of the function lowercase f, and I want to know the variation of that, okay, as I change f of x, I need to integrate over all space, because of course the function f of x changes everywhere. Right? So this is what's interesting about all this. So this is what makes it a little more complicated, but hopefully this screencast is going to help you understand this. Okay, now let's go to an alternative definition, which of course is going to be equivalent, but it will allow us to do some calculations because so far it's pretty formal, and we do not have a recipe really to calculate this functional derivative so far. So let's go here. Okay. Let's suppose now that we are making a change, an elementary change, epsilon, of the function f of x at every point. Okay. Actually, not every point, just at the point x equal y. So I hope you see this on the screencast. There is a little bump on in the middle there, which is at the position y. There is a little bump of amplitude epsilon. So this is a variation of f of the function, and what we want to know is that we may have a map from the blue function to another function, so what I call capital F before, and what we are interested in is what happens to the evaluation of this capital F function for this small variation of the function f of x. So basically, instead of the blue curve, we have the blue curve with the little bump at y. That's really what it is, right? This is how we calculate things. Now, if we consider this, what we are calculating here really is delta f. How does f change? Capital F changes. Now, the way it changes is, I mean, this is just obvious, this equation here, because the way it changes is what I have after the change minus what I had before the change, right? So far, so good. This is just obvious that we do that. So this is this operation of changing small f function changes the total f, right? Now we also know that the variation delta f is obtained by integrating over the entire space, and this is basically the definition I provided you a slide ago. So this is a definition I provided you a slide ago. So what I'm interested in, the functional derivative, is delta capital F over delta lowercase f, right? That's what I'm interested in. So we're almost there, actually, because we can continue doing this. We can say now that what I did in the last equation is simply replace delta lowercase f by my choice that I made on the top left, okay, which is epsilon delta x minus y. So I can do that, right? I can certainly do that, and I can calculate how the functional uppercase F changes. So as a result, when I put everything together, I find that delta F is equal to epsilon delta F over delta F of y. Why? Because I'd simply apply the rules of the integration with a Dirac delta, right? The Dirac delta here basically makes the integral only select the place where the Dirac delta is zero. So that means when x equal to y. So here y is a parameter, of course. So we end up with we obtain this result. Okay, so please, if you have trouble with this, pause the screencast and look at it. It's actually pretty elementary if we follow each step. It's just that we are not used to taking those steps because we rarely look at how a function of a function changes when we change that function. Okay, now if I identify this result with this result that I just obtained, now I can identify both sides, both right-hand side, and I obtain that the functional derivative, again, that's the left-hand side of this blue equation, is nothing else than the ratio between the difference between the function computed at two different places divided by epsilon. And of course here, just like we do in calculus, the small variation, because delta f has to be a small variation, is for epsilon at the limit of epsilon going to zero, and therefore I have my definition. Now you see this definition now, and I'm going to reproduce it on the next slide. This definition is very much reminiscent of what you're used to in calculus, in basic calculus of function. But the difference now is that the variation in the argument, the first term on the numerator, that variation is actually involves a Dirac delta function. Okay, so we take the limit and we calculate things here. Now the x value does not really matter here. You will see in some books that sometimes people simply put a dot because the x value is actually, that's true everywhere, so it's only a formal thing. So now what's nice is because this is reminiscent of what we learned for calculus of normal function, we will be able to apply the chain rules and so on, just like we derive from in basic calculus of function. Now, I'd like to tell you one more thing before we go into the practice of calculating these things, is that we can think a little bit away from calculus and maybe look at small increments. So like kind of if you want, working on a grid, okay? So that allows us to do something that, imagine that the function is really a function, instead of being a continuous function f, we have a function that's defined on a grid, and we have m values of f, which are noted. Those m values are noted at f of I going from 1 to m. And of course, when we do that, this is the same as saying that my new functional on the grid, if you want, so f tilde, is a function now, no longer a functional, but a function of a bunch of numbers going from 1 to m, so a series of numbers, which are the discretization of my function. And of course, it's simply a sum. And for this, we are used to this. I mean, we know that it's just simply a multi-variable. This is just multivariable calculus, the usual one that we are used to. And so how do we calculate the derivative of f tilde for each of the elements? Well, you're used to that. I mean, this is something that you are very familiar. It's just multivariable calculus because we go back to normal calculus. And this is simply obtained this is simply obtained by this function, where we are able to differentiate each term of the sum, because my delta there, I mean, for those who are confused here, my left-hand side of this equation is, of course, the gradient of f tilde, right? This is the notation of the gradient. And we can obtain each component of the gradient, and we can obtain this function. Now, the derivative, the partial derivative of f of I with respect to f of k is only non-zero when I and k are the same, of course. And therefore, this derivative, this element of the gradient is just 2f of k. Okay, this is just elementary. And now we can go backward and say that those m variables become continuous at the continuous limit. We can see that the functional derivative now is simply equal to these terms, right? Where I replace the derivative, the functional derivative by 2f of x, and I obtain is equal to 2fy. So the functional derivative of the integral of dx x squared x is 2fy when the functional derivative is, of course, calculated at point I, at point y. I am totally aware that this can be confusing if you've never done this before, and this is why there is a screencast. If it was obvious, I wouldn't do it. So we can wrap it up before we show examples. This is essentially what we did. So if you remember, the first equation is what you've done when you did your first day studying calculus. You actually calculated the first function on the top there. Well, maybe not the first day because it's partial derivatives, but maybe the second semester. And then you obtain this. And on the second row, just to show you the parallel between the definition, this is a functional derivative. It's a different notation. We're using a different delta. And in this case, we have to calculate things using the Dirac delta, delta x. So this is what we have. And so this is interesting because we can apply this now to any functional that we have. And in density functional theory, so this screencast is part of that series, we have lots of functionals. I mean, this is actually in the name, density functional theory. So everything is a functional of the density, and therefore we have many variations with respect to density, and this is why this is actually interesting. Okay? Now, I showed you simple example, but in general, the functional can depend not just of the density n or the variable, the function n, but also its derivative, second derivative, third derivative, and so on and so forth. And then the parameter, the usual variable x, and so on. So here I just have x, but I could have x, y, z, x1, x2, all the way to xn, and many values of x. So we can have all these. And there are definitions which I think it's important for people to know, especially in the context of this course, is that if the function f only depends on the density, we are then calling that a local functional, okay? If it also depends on the first derivative, we are calling a semi-local functional. And then if we have beyond the first derivative, then we call that non-local functional if they depend on all of those. So these are, again, definitions, but these are useful definitions because when you read papers on density functional theory and people say, we know that semi-local functionals overestimate bond length, now you understand that people really mean that the approximation that's made is using only the first derivative. So these are things that are part of the jargon and part of what you expected to know. Okay, now I'm going to show you a few examples just to try to cement this. First of all, let's look at the simplest case, which is the local functional. So on the top, you have the definition that we just came up with, the derivative. And so if you have a functional here written in black, it's a definition of locality, as I wrote in very small font there, which means that the function g is just a function of the function itself. There's no f prime in here. Now, if you do this, I invite you to plug in this function inside the blue box, and you will actually see that a few slides ago, it's exactly what I did. It was a local functional that I used as an example. Remember when I did f square, that was really what it was. You can directly find that the functional derivative in this case is simply dg over df. Now, it's interesting because in this case, when you have a local functional, really the derivative is what you're used to. Right? I mean, the variation of f with respect to f is just related to the variation of g with respect to f. So this is something that's not very surprising, really, because this is the local functional. Now we can have a semi-local functional. In this case, g in the integral is not just dependent on f, but also on f prime. And now this is where things are becoming a little bit more interesting. So again, I recommend to you, if you're curious, to pause screencast and really use this function within the definition in the blue equation to find that the functional derivative is the first term is the one we saw for local functional, but there is also another term that comes from the derivative. And this one is a little bit more surprising because there is a minus sign and it gives d over dx of dg over df prime, right? So this is actually something a little bit more surprising, maybe definitely more surprising for if you're not used to this, but this is there. And then you can keep going and apply the same for g, which would be not just f and f prime, but also f prime prime and so on and so forth. And you find a general formula, which is really the main thing that you have to learn is that that formula exists, and the formula is going to be in the red box here, in the box with the red dotted frame. And then you find that the definition of the rule, if you will, to calculate the functional derivatives is going to be obtained using this function. So that's actually all you really need to know. But I don't want this to look like a surprise or like magic. You can actually prove this term. Do not be fooled into applying the usual derivative when doing functionals. That's all I'm trying to also convey here. And I'd like to show you the example of the Hartree energy that I started with. So the Hartree energy, which is classical, really classical electrostatic energy, as we are going to see in lecture 3. So it's the interaction between interaction between the charge, the density. So imagine you have two electrons. You have the total density of electrons, and of course the two electrons interact in first order as these terms. Of course, we know that this is an approximation because there are terms in that functional, for example, the electron interact with itself, which we don't want. But let's not worry about the physics in this screencast. We'll worry about that in lecture 3. But the point is that the energy is given by this function, and the 1/2 is, of course, to avoid double counting, because if a charge at point R interact with a charge at point R prime, the charge at R prime interact with R, but we can't count that twice, right? So this function is a little bit more complicated, and it's a local functional, right? It's n and R prime. So we can calculate this functional derivative. Now, if you paid attention in your fundamental physics course, the derivative of the energy, okay, is a potential, right? This is what you saw not just in Coulombic interaction, but also in gravitational, in gravity, the gravitational potential. That the derivative, the potential is the derivative of the energy, and then you apply the rules that I gave you on the previous slide, and you will find that the Hartree potential is indeed given by this term. And I think it's important to see that this is not a super trivial result, really, because the two integral become only one integral, the 1/2 disappears. I will note that you did not have n square per se in the energy, but you have n over r and n over r prime. So this is a result that you can obtain using the equation before. Now, the best way to understand all this is to apply this to more examples. So here I selected a few examples for you where you can calculate the functional derivatives of those functional. So the first functional is, of course, a local functional. The second functional is not a local functional, right? So it's when we have the power n of a first derivative, and then the next term is actually also a local functional with some kind of kernel k, and the last one, the function of a function is just a function itself. So you can have an intuitive understanding of what's going to happen. So what I suggest you do, you try those, and then you go to the last slide of this presentation, which will give you the solutions. And the solution will be given by this. So you can either convince yourself that those results are what you would expect, or better, you do not look at this last slide and you do them first yourself and making sure that things are the same. I particularly like the last result, that if a function is a function or a function is a function itself, then the functional derivative is just the Dirac delta at that point. When you think about it a little bit, an intuitive pictures with using this little bump I showed you a few slides ago, that's a result that makes sense. So I think that I reached the soft spot of half an hour for a screencast. I shouldn't go much longer than this. I hope this was useful. Again, comments, questions, or anything, or how I can do this better if I ever create another version, are very welcome in the comment section. Thank you very much.